Rene 41 is one of the strongest superalloys obtainable in for use in the temperature range of 1200 degrees to 1800 degrees Fahrenheit. This simple statement becomes of vital importance when we realize that the nearest competitive alloys do not retain their strength at this elevated temperature, associated with the further fact that the jet engine afterburners heat their metal components to approximately the same minimum. In brief, Rene 41 is a superior metal for use in most of the jet engine afterburner components now on the drawing board. Rene 41 is a nickel-based alloy which achieves its strength through a precipitation hardening reaction. Major alloying constituents, in order of their abundance, are chromium, cobalt, molybdenum, and aluminum. Spectrographic analysis is performed on input material to determine its conformance to specifications. When conditions dictate, complete chemical as well as physical tests are performed. And is not determined by spectrographic means, but is ascertained by chemical analysis through the use of a combustion furnace and a carbon absorption chain. Material with high carbon content, even though within the specification, should not be used where severe forming or welding is required. Rene 41 does not lend itself to hydroforming as indicated by this experimental part. It is suggested that forms of this type be made by drop hammer in straight bends may be break formed satisfactorily. All material is received in a milled solution anew. In this state, sheet metal forming such as bending, breaking, and drop hammer cause Rene 41 to form in the same manner as 18/8 stainless steel. Increased power is required to form this new alloy because its yield strength and plastic memory are greater than 18/8 stainless. From the data accumulated to date, we find the material does not lend itself to compression forming, and all flanges should be properly beaded to protect the material in the contour. Several of these rings have been formed on the drop hammer at Ryan. Some were formed without benefit of an in-process anneal. On the unannealed parts, cracks occurred on the inner scorched flange. A part of this type should have at least one anneal during the forming operation. A Rockwell hardness reading should not be used as a criterion to determine if the annealing process is necessary, as this value is the operation and is not indicative of the degree of ductility. The solution treatment for annealing Rene 41 is accomplished through heating the material to 1975 degrees Fahrenheit for 30 minutes and subsequent oil quenching. The quench must be completed in a maximum of 2 seconds to obtain optimum ductility. A hardness comparison of oil quenched to air-cooled material illustrates the need for that quench. Air-cooled material has a Rockwell hardness of C23 or less, with elongation increased to 45%. The slower cooling allows the material to age harden, thus reducing ductility. Because this alloy has low warpage characteristics, the rapid cooling gives little distortion. The aging of Rene 41 is obtained by heating the material to 1975 degrees Fahrenheit for 60 minutes, followed by an air cool, and then reheating to 1650 degrees Fahrenheit for 4 hours. The aging process gives the material a room temperature strength of 155 pounds per square inch. Satisfactory descaling methods have been achieved using standard facilities. All material should be hardness tested after annealing. If a Rockwell reading C28 is obtained, the material should be re-annealed. Rene 41 is weldable by the inert gas arc welding process. When proper control is exercised over the influencing factors, the welds will be sound, ductile, and strong. For satisfactory welds, the following factors are considered necessary: good fit-up of parts, thorough cleaning prior to welding, rapid cooling of the weld area to obtain maximum ductility. This may be accomplished by the use of copper backup chill bars. The use of water-cooled welding fixtures may be necessary for some applications. Parts must not be underscrewed during welding. Information at the present time indicates that welding should be done with a material in the solution-treated annealed condition. However, tests at Ryan indicate that this procedure is not always necessary. Automatic should be employed wherever possible for best results. To maintain our usual high standard weld quality, all welds should be inspected by either the Zyglo or X-ray method. Assemblies will not be circled after the aging protocol. Where necessary, the loose scale may be removed from the weld with crocus cloth, a wire brush, or by vapor blasting to permit Zyglo inspection. As a test, a collar was formed and fusion welded. Subsequently, it was expanded 360 thousandths of an inch in diameter without evidence of failure. The part was expanded 8.9% of its original diameter. This was accomplished in as-welded execution. Rene 41 is one of the most difficult metals to resistance weld that we have encountered at Ryan. High tip pressure is required. The main problem being that the difficulty in achieving acceptable molded size. Weld samples were prepared for tensile testing. The samples were in two stages of processing, as-welded and annealed. The as-welded sample had a tensile strength of 22,000 pounds per square inch. The annealed sample had a tensile strength of 124,000 pounds per square inch. It's apparent that the difference in the weld strength between the as-welded and the annealed condition. Rene 41 may be machined without difficulty, even though it is less machinable than Inconel X. The use of high-speed tool steel in machining operation seems to have advantages over the carbide tip cutters. Rene 41 does not saw readily on do-all or slow-speed saws. Cutting may be accomplished on high-speed saws, such as the Tanowitz, which cuts by a friction process. Square shears or rotary shears, similar to 18/8 stainless. The material cannot be cut with a hole saw, and all holes must be drilled or punched. Careful consideration of the manufacturing 41, coupled with the good shop practices, which are standard in our manufacturing procedures, permit us to consistently produce parts to meet the exacting requirements of modern engineering, and to prove once again, Ryan builds better.